This video shows the commutation of a coreless DC motor with brushes. Based on an animation, it is shown schematically how such a DC motor is constructed and how the torque is generated. Or in short, what needs to happen so that the motor will operate. First, we have a look at the structure. Let's start with the cross-section of the stator. In the middle is a permanent magnet with a hole in the center. This hole is for the motor shaft. In grey color you see the motor housing. The permanent magnet is diametrically magnetized. The red upper half is the north pole and the green lower half is the south pole. The housing of the motor serves as the magnetic return. That means the magnetic field lines are guided through the housing of the motor. As a result, the magnetic flux is formed in the air gap between the magnet and the housing. The strongest magnetic flux is at the magnetic poles, in this animation on top and bottom. Next, we look at the rotor. This consists of two main elements: the commutator blade in the middle and the coreless winding in the air gap. The number of winding segments is always odd. In this animation we have 7 segments. This is a rather small number. A relatively high and odd number of commutator bars has two advantages: a reduced torque ripple and less brush fire, which increases service life and reduces electromagnetic interferences. To supply the power from the rotor winding, a brush system is required. The brushes are supplied with DC voltage, symbolized in our animation with a small plus and minus. On the present position of the rotor, the brushes are connected to the commutator bars 1 and 4. The electric current can now flow through the winding. If we analyze this current flow in the winding, we can see that on the opposite side of the winding cylinder, two opposite rhombic-shaped current areas occur. Since these current areas are located in the magnetic field of the stator, forces are generated, so-called Lorentz forces. These forces lead to a torque in a counterclockwise direction. The rotor starts to rotate. After a few degrees of rotation, the minus brush moves from commutator bar 4 to 5. In most of the segments, the direction of the current remains unchanged, with one exception. In the winding segment between the commutator bars 4 and 5, the direction of the current changes. As a result, the center of the rhombic-shaped current area, which is being built near the minus brush, shifts. With this shift, the rotor can continue to rotate at the maximum possible torque. After a few degrees of rotation, the positive brush switches from commutator bar 1 to 2. This process is called commutation, because the current flow in the corresponding winding segment changes its direction. Accordingly, the center of the rhombic-shaped current area near the positive brush shifts. The rotor continues to rotate and commutates alternately once at the plus and once at the minus brush. After 14 commutation cycles, the rotor has made a complete revolution and is back at the initial position. Now you know how the commutation of a brush DC motor works. On our website maxongroup.com you can find more information and videos, such as the commutation of brushless DC motors. Thank you and goodbye.